great pleasure for us to make a presentation here in new format. So today is the first time for us to make a presentation in Security Analyst Summit online session. So today we will talk about a new zero-day exploit that we have discovered several months ago. So we will provide deep technical information about how this zero days were spread and what techniques threat actors used. So today my first speaker will be Boris. He is a senior security researcher in the Global Research and Analysis team. So let's start. So for the last year, we have discovered a lot of zero days in Microsoft Windows operating systems, and all of them were used in highly targeted attacks against several victims. So, and in the end of the last year, we have discovered two new zero-day vulnerabilities. And what was interesting that it was a real watering hole attack against the Google Chrome browser. So we have discovered a zero-day exploit in the Google Chrome browser. So, at the end of October of the last year, our exploit detection component has successfully detected exploitation process in the Google Chrome browser. So it was a really interesting finding that we start to investigate this case. So during our investigation, we have discovered that it was a real watering hole attack. So the legitimate news resource, web resource was infected. So, and we have found that it was a really legitimate resource, and there was a malicious injection. So in this slide, you can observe a little script that was injected to the legitimate web page. So the landing page consists of several lines of code, and they were loading the second stage from the threat actor's infrastructure. So what was interesting? During our investigation, we have found that victims with Google Chrome were targeted. So it was really interesting finding because we haven't seen it before. So, and we start to analyze the second stage script. So, and we have discovered that this script was downloading the malicious exploit from another threat infrastructure. It was encrypted, and it was delivered in several chunks, which were decrypted directly in memory and loaded in it. And we have analyzed this process and discovered the full chain which was used in this attack. So, Boris?
Hello, everyone. It's really nice to have all of you attending our presentation. So, yeah, we received this next stage, and we analyzed it. We found out that it was really huge in size because it contained a number of byte arrays. And, well, there was a WebAssembly model. It was used at later stages of exploitation. And there was also byte arrays with shellcode and actual next stage that was used after successful remote code execution exploit. So right on the start, this exploit, it was performing checks for current version of Google Chrome. And exploit, it was targeting only versions 76 and 77. But when we analyzed it, this exploit, we found out that the latest versions of Chrome, which was build 78, it was also vulnerable. And as soon as we realized that, we shared this information with, along with proof of concept for this vulnerability, we shared them with Google Chrome security team. And they assigned it CV number and fixed this vulnerability. So this vulnerability, it was a bug in web audio component. It was a use after free, and it was possible before the patch. It was possible to trigger this use after free because of race condition that was present between renderer and audio threads. So here you can see the commit that fixed this vulnerability, and also you can see the official commentary from developers. So this vulnerability, it was present because before the patch, it was possible to nullify the buffer in one thread in audio, while it's still in use in renderer thread. Well, there was no proper synchronization between threads. And so it's classical use of free. And this vulnerability was fixed with the developers. They added a proper locking for two buffers. And let's talk about exploitation. So we were able to fully reverse engineer this exploit and find all the details about it. And I've got to say that exploit writer, he has a perfect knowledge about internals of Google Chrome, and especially about allocator, which is used in this web browser. So Chrome uses Partition Airlock allocator, and exploit, it has a number of primitives. Well, some of them are not used, but present. Probably developer used them while he was developing this exploit. And so these primitives, they used to get some very important structures that are present in this allocator, like super page address, partition page address, index of partition page inside super page, and etc. Well, different metadata and so on. And what is also interesting is that this exploit, it uses a quite new built-in class that called BigInt. It's used to work with 64-bit numbers. And well, previously in all other exploits, we just saw exploit developers to use their own primitives to work with 64 numbers. And it's interesting that right now they have a built-in feature that they can use while developing exploits. And well, exploitation is quite tricky because actually vulnerability is triggered not once, but twice. And during the first trigger, it tries to leak the pointer to some object. And well, what is interesting about Partition Airlock, how it's different from other allocators, is that it has a special exploit mitigation that works like this. When a buffer is freed, then the pointer of it, it's byte swapped and put into free list. And so when exploit will try to dereference this byte swap pointer, it will lead to crash of the process. So it will stop exploitation. So this exploit that we found, it has some heuristics to determine if exploit was actually byte swapped. So this way it's able to bypass this exploit mitigation. So at the first time when it successfully runs exploits vulnerability, it leaks some pointer. And then during second vulnerability trigger, it tries to use this pointer to reclaim memory that was freed during the first run. And also defragment heap, it wants to get heap into a valid state to not get it to crash at some stages later, because it still needs malware to run. Yeah. So when after these two vulnerability triggers, it also creates a big WINT64 array, and it will be used later to get read and write. And it actually manipulates partition page metadata to actually build this primitive from big WINT64 array. And when exploit achieves readable, writable primitives, there comes a time to get code execution. And to do that, previously mentioned WebAssembly Model is used. Because currently in Google Chrome, when WebAssembly Model just-in-time compiled code is compiled, it's allocated, memory for it is allocated as with readable, writable, and executable permissions. So in case if you're able to get pointer to this just-in-time compiled code, you are able to simply overwrite it. And this is exactly what exploit tries to accomplish. So on this slide, you can see the WebAssembly Model, the compiled code of it that is present in exploit. You can see that it's just it's just filled with dummy instructions that are trying to increment some values, some local variables. And exploit developer just needed some huge WebAssembly Model to have enough space to put shellcode in. And this model is executed with file reader object. And so when file reader object is created, it creates some other objects internally. And in case if you have a possibility to, in case you know what the address of the next object that will be allocated, what the size of next object that will be allocated, and you're able to parse the structures of locator, then you can predict at what address this object will be located. So, and from there, if you're able to have access to different objects and you're able to parse that, you are able to get the pointer you're able to get address where the shellcode, address where just name compiled code will be allocated, and you will be able to write it. So on this slide, I provide snippets of code that are used in exploit to get this address. And of course, in exploit, all these variables, they were obfuscated. We were able to find the real names just by doing our reverse engineering work. And let's talk about shellcode. It's a quite simple portable executable loader. It doesn't have any extra functionality. All what it does, it executes an additional module that was present in exploit. And well, as this additional module, it was elevation of privilege exploit. Well, it exploited the Win32k vulnerability, and well, I always wonder how many more words can be said about exploitation of Win32k. But then later we find one more zero days that exploits Win32k, and well, according to Microsoft, Win32k, it's the component that is responsible for almost 50% of all kernel vulnerabilities. But still, we continue to find more zero days that exploit Win32k. In just last 2 years, we probably found maybe 4 or 5 zero days for this component. And well, some of them support the newest builds of operation system, but the majority of them target only older builds of operation system. But it also indicates that customers have really tough times updating their operation systems, even just the newer builds of Windows 10. And well, this vulnerability, it was present in SetWindowLongPointer. That it's a syscall that is present in Win32k driver, and it has a quite of history of different vulnerabilities related to it. So in Win32k, a few important objects are represented by tag window structure. It's well, and to distinguish these different objects, there is a special field. It's called FNID. So depending on this field, driver knows what type of the window it is. Like it can be a regular window, it can be a scroll bar, or menu window, or tooltips window, or desktop. And what is different between all these types is that, well, they have a tag window structure, but depending on the type, they may have different extra data associated to it. It's usually just some another structure that is appended to tag window structure. And the SetWindowLongPointer function, it can be used to write this extra data. So, but of course, it's performed only after validation that it's possible to do that for this kind of object. But in case of CV 2019-1458, this validation, it was just insufficient. Well, you can on this slide, you can see the logic that will prevent this bug. But in case of this vulnerability, the values to check for actual check for 3 types of objects for desktop, switch, and tooltips, like the values for the check, they were just not initialized. So it just was possible to write any field of extra data for these 3 types of objects. And of course, these objects, there was some structures with kernel pointers. And for exploitation, like it's possible to use message call, syscall to address, to execute any window procedure if you provide the right type. So the first, it's executed to make a regular window to be a switch window. And then user SetWindowLongPointer function is used to override some pointer of switch structure with some other arbitrary kernel pointer. And then if you use message call again with a special message type, it will lead to the reference of this pointer that you was able to set previously. So here provide 4 instructions, and it's possible to use them to increment or decrement some arbitrary value. And well, exploitation it's performed with the use of bitmaps. It uses 2 different kernel SR bypass techniques. In case of Windows 7 and first build of Windows 10, it leaks bitmap addresses via GDI shared handle table technique. And in case of Windows 10 build 14393, at first it's a very common technique. At first it's create accelerated table, then it leaks its address via GDI shared handle table, and then frees this accelerated table and tries to allocate bitmap using the same freed memory. So it's fair to say that this technique was patched in modern builds of Windows 10. And for exploitation, it uses another technique that was mitigated in Windows 10 Redstone 4. So bitmaps in Windows case are represented by surface objects. So they have the following structure, and in case if you are able to allocate 3 bitmap objects, you're able to allocate them next to each other, and you're able to corrupt with vulnerability the size of pixel data buffer. Then you will get out-of-bounds write access to the next bitmap, and from there you're able to corrupt the header of next bitmap. You're able to set your own size and pointer for pixel data, and from that it's possible to use 2 functions that are called set bitmap bits and get bitmap bits to just read and write any data from kernel memory as if it was pixel data. And so that's what exploit does. And when it achieves readable, writable primitives, it just steals system token. This is technique that we see like in 99% of all exploits, all elevation privilege kernel exploits. And after that, after achieving these system privileges, it finds the string that was packed from JavaScript. So it just performs search for the signature in the whole memory of the browser, and then it fetches the data by the following URL, and it also uses RC4K. So you can see that this URL it points to the GFI image, and if you will take a look at this image, like at the bottom of it, there is a encrypted payload. And the last double word, it actually indicates the size of this payload. So it gets decrypted with RC4K that was got previously, and it results in another URL of another image. But it's also not really an image. It's portable executable without MZ magic and encrypted with SOR. So exploit this final stage, it just decrypts it and appends MZ magic and drops it to temporary folder as updata.exe. And here comes the time to talk about this final payload. And Anton will tell you more about that.
Thank you, Boris. So what about payload? As Boris said, after successful exploitation, a malicious binary is dropped to the folder and executed. So after our analysis, we found out that it is a simple self-extracting archive which contains several malicious modules. So and the main payload was located in the special handler which executes after the payload was successfully started by browser. And what it does, it creates several task scheduler tasks. So please pay attention to this slide if you will find such indicators of compromise on your machine, so you might be a victim of this targeted attack. So each task is created with interval for 10 minutes, and so after it tries to execute it. And what was interesting about this payload? So it tries to download several stages. Unfortunately, we have no all of them. And what was interesting, that how threat actors were downloading these stages. So it was a simple algorithm. So it just runs several URLs. So and tries to download the second stages. So they were located at the threat actors infrastructure as pictures, but as malicious models. So also interesting fact that the path to the malicious binaries contains computer name of victims. So it might be threat actors knew about the victims a lot of information, so they can locate this binary, so they can just distribute it to several IP addresses, for example. So unfortunately, we have no such models. So and why we have no such models? Because as I said, our exploit prevention component successfully stopped the exploitation process, and we haven't received the further stages. So if you have those stages, so you can share it with us, and we will continue our analysis of this threat actor. And what about false flag? During the analysis of the code of malicious binary, we have found that several pieces of code were similar to Lazarus Blue North malware, but we think that it is a really false flag. So, and it is very interesting who is behind of this attack. So we continue to investigate this attack, and if we will find more malicious models or watering hole attacks, we will share this information with security society. And in the conclusion, we want to thank the Microsoft and Google, because they have done a great job. They fixed the vulnerability in a very fast way. Also interesting fact that Google has provided a bug bounty pay for us, and we receive to donate it to the charity organization. So Google doubled the money, and we have provided it to the famous charity foundation. So thank you for your attention. If you have any questions, we are ready to answer them right now, or after presentation you can contact via Twitter with us. Thank you.
Thank you very much, Boris. Thank you for your fantastic presentation. Thank you for all your work finding these 0 days and keeping the ecosystem safe. A couple of quick questions, because we have some time for questions. What makes the majority of the days today, the 0 days that you guys are finding, only supporting older Windows versions? Are there like some new mitigations that are causing this?
So, of course, Microsoft and other vendors are implementing a lot of mitigation algorithms to their software and operating system. But unfortunately, threat actors can find some ways to bypass this mitigation techniques. But please pay attention that every new 0 day is a very hard scheme. So, for example, now a lot of remote code execution 0 days are providing with local privilege escalation, because threat actors should bypass such mitigations like sandbox and other mitigation techniques. So it is very hard now to use the vulnerabilities, but unfortunately we observe that threat actors are still using them, and we think that threat actors will continue to use it against the victims in targeted attacks.
What threat actors account for the larger trend of 0 days you guys are uncovering? Is there a specific threat actor?
We observe that different threat actors are using 0 days, so they invest a lot of money to this. So they have some of threat actors have dedicated teams which are researching and tries to find new 0 days. Some of them are buying it on the black market, so they invest a lot of money on this. So you need a proven security solution.
Given the code similarity false flags that you mentioned, who do you actually pair WizardOpium with? Have you guys been able to connect it with any other activity?
So we are currently investigating this issue, and we are continuing to research this threat actor. So currently we can provide the information with whom they are connected. But there are some information in the open in the internet, so you can read it. But we still are investigating this threat actor.